Hello, I'm Xingyun Chen. This is a recording of the 5th exam preparation section. As always, if you have any questions, feel free to come to my office hours. It is 3 to 5 p.m. every Thursday. This week, we will discuss questions about probability. So let's take a look at the first problem. So from the problem description, we see that it defines 5 random variables. Well, A, B, C, and D are Boolean random variables, which means that they could take 2 values. Then for the variable E, you could take 5 possible values. Then question I is asking how many entries are in each probability table and what is the sum of all the values. So basically the size of the probability table means what are the number of probabilities we define for each probability table. So it depends on the number of different values that could be set for random variables. So before we go into the actual questions, let's clarify the notations first. So basically for capital letters A, B, C, D, and E, they mean random variables. But when we use the lowercase letters, they mean that we have already set some values for the corresponding random variables. For example, for the first probability table, it means that we already set the a value for the random variable E, but for the random variable B, it could take all the different values. So basically means that for this probability table, its size is 2 because there are 2 probabilities to set. The sum of these 2 probabilities is unknown because we have no knowledge about what's the probability of E given the value of the random variable B. But then for the second table, probability of C of A and B given C, then when we sum over all the possible assignments of A and B, its value is 1 because we enumerate over all possible assignments here. So based on the discussion of these 2 probability tables, we will be able to fill in the answers for the remaining probability tables. So let's take a look. So as we discussed before, for the first probability table, its size is 2 because there are 2 assignments of the random variable B. Its sum is unknown. Then for this, we can kind of take a look at the size first, because for the size of different probability tables, it only depends on the different assignments of the random variables. So for the second probability table, we know that both A and B could take 2 values. So the size of this probability table is 2 times 2, which is 4. For the third probability table, again, its size depends on different assignments of A, B, C, and E. So there are 2 options for all of A, B, C, and there are 5 options for E. So the size should be 2 times 2 times 2 times 5, which is 40. Then for the fourth probability table, we need to consider different assignments of B, C, and E. So the answer should be 2 times 2 times 5, which is 20. Finally, for the last probability table, we need to consider different assignments of A and E. So it should be 2 times 5 equal to 10. Then according to our previous discussion, the sum of all probabilities A, B given C should be 1. Then for the third probability table, note that for all assignments of C and E, its sum of probability should be 1. Therefore, when we consider all the possible assignments of C and E, there are 5 times 2 equal to 10 different assignments. So the sum here should be 10. For the fourth probability table, the sum is unknown because we have no knowledge of the probability of A given BC. Finally, for the joint probability of ACE, its sum will be the same as probability of C. And if we assume that we know nothing about the probability of each random variable, then again the answer for this part is unknown. For part II, it is asking about the minimum number of parameters needed to specify the distribution. So here it means that how many probabilities we need to specify so that this distribution is kind of complete. So we recall that from our previous discussion, for any assignments of C and E, the sum of probabilities A, B given C, D, E is 1. So basically, it means that because both A and B are Boolean variables, so there are 4 different assignments of A and B in total, if we consider all the possible assignments. But since their sum is 1, so it means that once we know 3 of these 4 probabilities, the last probability is given by subtracting the sum of the remaining 3 probabilities from 1. Therefore, to fully specify the distribution of P A B given C D E, so for each assignment of C and E, we only need to specify 3 probabilities. And when we multiply it by all possible assignments of C and E, there are 10 choices. So finally, the answer should be 30. For part II, it is still asking about the minimum number of parameters. But recall that from part I, we already know that the sum of probability of AE given BC is unknown because we have no knowledge of probability of A given BC. Therefore, we still need to fully specify all the probabilities, where there are 20 probabilities as we discussed before. Then for part B, it asks us to simplify the expression. But since we have no further assumptions of the independence, it means that we can only use the chain rule to simplify the expression. So let's take a look at part I first. So according to the chain rule, for any given A prime, probability of A prime given BE times probability of C given A prime BE is a probability of A prime C given BE. By summing over all the possible A prime, the answer becomes probability of C given BE. For part II, similarly, we can first use the chain rule to know that the numerator should be probability of BC, and the denominator should be probability of C. Then, according to the definition of conditional probability, this is the same as probability of B given C. Then, for question 2, it is mainly asking us about how to apply the chain rules and also to use the assumptions about independence and conditional independence. So before we dig into the problem, let's do a brief review of independence and conditional independence first. So basically, if we say that A is independent of B, it means that probability of A given B is the same as probability of A, and probability of B given A is the same as probability of B. So it means that adding the knowledge of another variable does not affect the probability of the current variable if they are independent of each other. If we say that A is conditionally independent of B given C, it means that probability of A given BC is the same as probability of A given C. And the probability of B given AC is the same as probability of B given C. So it means that with the given variable, if two variables are conditionally independent, then it means that we only need the knowledge of the third variable C, and with this knowledge, adding the knowledge of another conditionally independent variable does not affect the probability. So with a brief review of the concepts of independence and conditional independence, let's look at the actual questions. So for part I, it is asking us to compute probability of AB given C with some knowledge of other probabilities. And here we have no other assumptions of conditional independence, which means that we can only use the chain rule to compute the probability. So let's see. So according to the chain rule, probability of AB given C is equal to probability of A given C multiplied by probability of B given AC. However, we only have a knowledge of probability of A given C, because we do not have any assumption of conditional independence. We cannot represent this probability with the given probabilities. Then for part II, according to the definition of conditional probability, the probability of B given AC is equal to probability of A, B, C divided by probability of AC. So to compute the probability of ABC, it is equal to probability of A multiplied by probability of B given A, then probability of C given AB. Then to compute the probability of AC, it is equal to like summing over all possible values of B. Then so basically it means summing over all the possible B, then C ABC. So which is summing over B, probability of A, probability of B given A, probability of C given AB. So basically, this is the final answer. Then for part II, it is so to compute this probability using the given probabilities, here there's an additional assumption saying that probability, so basically A is independent of B. So this effectively means that probability of A given B is equal to probability of A, and vice versa, probability of B given A equal to probability of B. So to compute probability of C, it is equal to summing over all A, then probability of AC. According to the chain rule, it is summing over A probability A times probability of C given A. And according to the independence, it is equal to probability of summing over A, probability of A given B, probability of C given A. So this is probability of A given B and probability of C given A are from the problem description. Finally, let's see how to compute probability of ABC. Here we have an additional assumption of conditional independence. Then let's see. So to make the best use of the probabilities given in the description, it should be probability of B multiplied by probability of A given B, then the probability of C given AB. So both probability of B and probability of C given AB are from the problem description. However, in the problem description, it only gives the probability of A given BC, but not the probability of A given B. But from the conditional independence, we can only know that probability of A given BC is the same as probability of A given C, but we have no knowledge of probability of A given B. So the answer for part IV is still not possible. Then for part B, it is asking like to basically to make the left and right hand sides equal. What are the minimum set of conditional independence we need to assume? So let's take a look at part I first. So according to the definition of, according to the chain rule, probability of AC is equal to probability C multiplied by probability of A given C. So basically to make the left and right hand sides equal, we need to make sure that probability of A given B is equal to probability of A given C. So the idea here is that if A is independent of B and also A is independent of C, then basically here we can have both of these two probabilities are equal to probability of A. Then the equation becomes true. Then for the second part, according to chain rule, according to the definition of conditional probability and the chain rule, so the left-hand side is equal to probability of ABC divided by probability of BC. Then, according to the chain rule, it should be probability of C multiplied probability of B given C, probability of A, probability of B given A, probability of C given AB. So to make it equal to the right-hand side, we need probability of C given A to be equal to probability of C given AB. Then this basically means that given A, the knowledge of B is not required to compute the probability of P or of C, then basically it means that B and C are independent given A. Then for the third part, actually probability of AB is equal to probability of ABC when we sum over all the possible values of C. Then it means probability of C, PC, probability of B given C, and probability of A given BC. This is according to the chain rule. So basically, for this equation, no independence assumption is needed. Then for the fourth equation, actually it also naturally holds according to the chain rule. So basically, it is probability of it should be probability of A, B, C, D divided by probability of C, D. So probability of B, probability of C given D, according to the chain rule, probability of B, probability of C given D, probability of A given CD, probability of B given ACD. So divide these two terms, we get probability of A given CD times probability of B given ACD. So again, here, no independence assumption is needed. For part for the problem I of part C, let's see which expressions are equal to probability of A given B without additional assumption of independence. So first we can see that for this term, it is summing over all the possible C. It is indeed equal to probability of A given B. So this choice is correct. Then for the basically for this item could not, the first item could not be correct because it also it basically here the probability is conditioned on additional things, and it is not when we have additional condition of C to compute the conditional probability of A, it is not equivalent to probability of A given B anymore. Then that's so for the second term, it is also not correct. Let's do some derivation, and actually it should be like, So we see the probability of AC given B should be probability of C given B times probability of A given BC. So so basically this term should be equal to this term, which is not equal to probability of A given B. Then for this term, it is well, for this term, it is also not correct if we try to like if we try to do some derivation. Then for this term, it should be the numerator should be so this term is also not correct. Then finally for the last term, it should be equal to the denominator should be probability of B when we sum over all the possible C. Then the numerator should be probability of AB. Then according to the definition of conditional probability, it should be probability of A given B. So this is correct. Then for part II, we need to compute the probability of ABC, given that A is independent of B. So for the first term, let's see if this is correct. So P, A, B, C, according to the chain rule, it should be probability of B, probability of C given B, and probability of A given BC. So for the first item, basically we need to compute the probability of A given C with probability of A given BC. But these two are not necessarily correct, because from the independence of A and B, we only know that probability of A is equal to probability of A given B, but we have no knowledge about how we compare probability of A given C with probability of A given B and C. So this is not equal. Then let's see if the second term is equivalent. So let's use another way to compute the joint probability. So PABC equal to probability of A, probability of B given A, probability of C given AB. So this is effectively the so according to the chain rule, it is exactly the same as the second term. So this is correct without any additional assumptions of independence. Then because we say that A is independent of B, so it means that the probability of B given A is the same as probability of P B. So this means that the third choice is also correct. Then for the fourth item, again, it is correct according to the chain rule. Then for the fifth item, let's see whether it is correct. Then yeah, we can then again another way to compute this joint probability. Should be probability of C B given AC. But again, we need to compare this probability of B given C with probability of B given AC. But it is but this equivalence is not given in the problem description, so this is not correct. Then for the last item, we need to compare probability of B given C again with the probability of B given AC. It is still not correct. So basically for part II, there are three expressions that are equal to the joint probability of ABC. Then finally, let's compute the probability of AB given C, given that A and B, A is independent of B given C. So again, firstly, we can know that probability of AB given C is equal to probability of A given C multiplied by probability of B given AC. This is according to the chain rule. But because A is independent of B given C, so this means that the probability of B given AC is equal to probability of B given C. Therefore, the first choice is correct. The second choice is equal to probability of AB divided by probability of C. Then without additional assumption, this is not equal to probability of AB given C. Then another way to compute probability of AB given C is according to the definition of conditional probability. It should be probability of ABC divided by probability of C. So it should be probability of probability of B times probability of A given B and probability of C given AB. So the last two terms is equal to probability of CA given B. So the fourth choice is correct. But then for the for the third choice, because actually it is equal to probability of ABC divided by probability of AB. So it should be probability of C given AB. So this item, so this is not equal to probability of AB given C. So this is incorrect. Comparing the fifth item with the first item, because the probability of A given B is not necessarily the same as probability of A given C according to the problem description, right? So it means that the fifth choice is not correct. Finally, to verify the last term, if we do some computation, like so it's probability BC according to the conditional independence, it is the probability of A given C is the same as probability of A given BC. So it is probability of A, B, C divided by probability of C given AB. So this is the probability of C given AB is not necessarily equal to probability of C given a problem description. So the last item is also not correct. So finally, there are two choices for this part.
That's it. Thank you. If you have more questions, feel free to come to my office hours.